Okay, welcome everyone. So we're going to talk about something called residuality theory, which is quite an exotic term and a new idea. And it's an idea that has its roots going back 10 years and trying to teach software engineers, how do we design systems? What is it that happens in our heads when we design systems? And why is it so difficult? And why is it so difficult to teach? And it is a new idea, and it's the basis of my PhD project within the complexity sciences and software engineering. And so the problem that we're trying to solve is, why is software architecture so difficult? Why is it so hard? Why is it so hard to teach? And so research studies done in 2016 have shown that when you ask a senior software engineer or an architect, why did you make the decisions that you made? Why do you have 3 components, not 2, not 4, to solve this particular problem? Nobody actually knows. And it goes a lot in gut feeling. But also, whenever we're forced to answer that question, it feels uncomfortable to admit that everything goes on gut feeling, because we feel like we should be proper engineers and we should have like some math or something that shows us that this is the problem. So what is the problem? What is it that makes this so difficult? There's 3 fundamental things that will come along and destroy your architecture and make it difficult, and it makes us afraid. And those things are time, change, and uncertainty. And we deal with these things by simply sweeping them under the rug and pretending that they don't exist. So if you look at the standard way that we represent our architectures and communicate our architectures, UML, Archimate, scrolling on a whiteboard, we don't have any way in those diagrams to represent time, because architectures are not static. The architecture that you deliver will change as the project moves forward. And the reason time is important is because things change. So it's not static over time. And the reason that time is so change is so troublesome to us is that we don't know what's going to change over time. And therefore we can't represent these things, and we end up representing a static picture of what the architecture might be, in the knowledge that that static picture is going to be proven wrong very, very quickly once it hits cold, hard reality. A second problem we have, that we haven't really solved yet, but we've been trying, is the question about the unit of software engineering. What is the unit of software? This maybe seems like a strange question. So if we go all the way back to ancient Greece, they've thought about, what is the unit of our world? What is the building block? What is the thing that makes the world? And they had theories that there was earth and fire and wind and water. And over the years, we've developed different theories. Physicists see the atom or the Newtonian particle as the building block of the universe. Chemists see the molecule. Biologists see the cell. What do we see as the unit of software? Well, it depends who you ask. We've had a bit of a history here, and it's still ongoing. Started with machines, then it was the punch card, then it was the objects. God help us. We moved to services, and then we tried to and quantify and make units out of the human systems around us. And we talked about things like capabilities and processes and features and all of these things. And we've never really arrived at a satisfactory answer. And every generation feels the need to create 3 new ones. And that's what we're going to do here today. So the unit of all of these units of software engineering, of software, all of them fail to capture this fundamental thing: time, uncertainty, and change. And so this will introduce a new concept, the residue, which is going to capture these 3 things in our architectures. Before we go any further, we need a few definitions that are vitally important to understanding the world that we work in. The first is the difference between order and disorder. So some systems are ordered. And an ordered system is a system in which the actors in the system are highly constrained. They can't really do what they want. They don't have a lot of wiggle room. And because of this, it makes them predictable. And because they're predictable, we can test them. And you can see that they have roughly the same behavior over testing cycles. And so software, by this definition, is an ordered system. You'll hear people say that software is complex. It's actually not. On the other hand, we have disordered systems. And disordered systems, the agents inside the system are loosely constrained. They have lots of freedom. They can move wherever they want. They tend to be unpredictable because of this. And they'll have changing patterns. You'll think you see a pattern and then it'll do something different, or no patterns at all, which is overwhelming for us as engineers. And human and business systems are most often disordered, although we do a good job of pretending that they aren't. And this is where the problems for a software architect start to appear. Our job as software architects, so designers of software systems or senior developers, is that we have to build a structure. And we have to say that it's got this many components and they run on this platform and they live over here and they talk to each other this way. And that's the structure of a software application. And that's our job. And what we do is we take this innocent, tragic little thing and we put it into an environment that we call a business that exists within a market, that exists within a society, that plays by the rules of an economy and has politics and all of these things that are moving and churning and constantly changing. And so what we're doing is we're putting an ordered system inside a disordered system. And the first thing that happens is that the disordered system will tear our innocent, tragic little architecture to pieces. And this is what we've been doing for 60 years, and we keep going, why is it so hard? And what happens when you put this innocent little thing into this vicious bubble of noise is that this thing turns up, X. We don't know what X is. We don't know when it's going to turn up. We don't know why. And it's never alone. There's always loads of them. And they turn up, and as soon as they turn up, we get surprised in the business environment. And then they tear our architecture to pieces. They put pressure on it and they reveal that this structural decision was wrong and this should have been 5 components, not 2. And why did you do it like this? And this is very, very difficult. It sounds almost impossible to solve. And the way that traditional architectural methods like enterprise architecture have tried to solve this is just to make the bubble smaller and pretend that reality is actually easier than it is. And we can just map some processes and some capabilities, and we have a scope, and we can restrict everything. And we as software engineers will only work with the X's that our business stakeholders define for us. And if they haven't defined it, then it's not part of reality. And this is a fantastic business model because we get paid again whenever it blows up. And maybe we should be quiet about that, but I can't help myself. The problem with this model, of course, is that reality never goes away, and eventually X pops up again, and we suffer the same issues. And we do all kinds of things to get away from it. Call it technical debt and pretend it's not there, or just patch things. And if things were really as bad as what I've just described, there would only be one solution to this problem, and that solution would be to work in an agile way and do nothing until X shows up, and then just react. And we've seen, in a lot of cases, where that doesn't work out so well for the architecture of a system. But it turns out there's another problem here, and that is that there is a group of senior architects in the world who consistently build solutions that get out of this. They don't suffer from this problem, and they make it difficult for the rest of us because everyone then points at our work and says, why can't you do it like them? And so we have to answer the question, what are they doing? How are they doing this? What are they doing that's different, that allows their system to survive in an environment and lots of other systems don't? And the one thing we can say is that they cannot predict the future. If you ask them, how do you do this? They will say it's because we're magic. That's not what's happening in most cases. And so trying to answer this question and trying to figure this out led me to engage with something called the complexity sciences, which is this very obscure scientific discipline, which is pretty far away from what we've done in computer science. And the question is, how can we make this relevant to software engineering? And so to get a glimpse of this, what we're going to do is we're going to look at software architecture from the perspective of the complexity sciences. And it turns out from their perspective, software engineering is pretty easy. Two tools from the complexity sciences that are important to understand what it is that we do as software architects from their perspective. The first is random simulation. Random simulation works like this. I have a problem, but I don't have all the information, and I don't really understand what I'm working with. And so the problem I have is that I have a square of side x, and the problem I want to solve is, what is the area of the circle? If you ask someone who's had high school math how to solve this problem, and most of us will start to look for the radius of the circle so that we can do that pi r squared thing, and everything should be nice and neat. But that's not how life works. In this example, you can't figure out what the radius of the circle is, so you can't calculate the area. And so what we do in the complexity sciences is we just throw a dart at it. And the first dart I throw hits the circle. And the second dart I throw misses the circle. And based on my data set, the circle must be half the area of the square, which is x squared over 2. I heard some of you laughing because it feels ridiculous. It turns out that if you do this with 2 darts, is kind of ridiculous. If you do this with a lot of darts, you get very, very accurate answers about the area of the circle. And not only that, you free yourself from knowledge of the shape, because it doesn't matter if it's a circle or not. This will give you an idea of the area of the thing. Think about when you do requirements engineering or risk management, or you try to talk to business people. How is it any different than throwing random darts at a shape? You meet a random stakeholder on a random Tuesday, and you say, how does this process work? And they make up a random answer because saying, I don't know, is not an alternative. and so random simulation is how we deal with huge, uncertain systems where we don't know exactly how the system works. We don't know all the rules, and we've no scientific basis on which to make our decisions. We just poke it. It's a very unscientific term. The second concept in the complexity sciences that's absolutely vital, and probably the most important result in the complexity sciences, is a concept called Kauffman networks. And Kauffman was a biologist who worked in the 1960s. And he was trying to figure out, how did we get from a big ocean full of amino acids, how did we get from that to the beetles? How does that happen? And he did it with this concept, very simple concept of a Kauffman network. And a Kauffman network is also known as a random Boolean network, an RBN. And it's Boolean because every node in the network, and every little circle here is a node, every node in this network is Boolean. It has 2 possible values, 1 or 0. And the way to imagine these networks, which will help you understand this example, is to think of them as light bulbs, because they're either on or off. And so I have a little button here beside the network. Every time I press this button, these things get a signal. And they're random because inside every light bulb, there's a little bit of code. And that little bit of code decides when it gets a signal from this button, it runs and randomly decides, am I a 1 or am I a 0? So every time I press this little button, I'll get a new pattern of light. And Kauffman did this with 100,000 light bulbs, which is a lot. Virtual light bulbs, right? His house wasn't that big. The number of possible states for this network is 2 to the power of n. When n is set to 100,000, as Kauffman did, this number is enormous. The number of possible states in this system is larger than the number of known atoms in the universe. But these are binary nodes. A human system, a business inside an economy, is actually worse than this. And at this point, gathering requirements seems like a very strange idea indeed. Then he did something else. He added links between the nodes. And he made it possible for a node, when it executed its little function, he made it possible to communicate to one of its neighbors its result. It said, I'm a 1 or I'm a 0. And its neighbor would then take that message and recalculate. So that when you press the button now, you'll see a little bit of flashing. And then it'll settle down into a pattern. And he noticed something strange about this. He noticed that the system kept coming back to the same patterns over and over and over again. So for the original network, you would have to press that little button probably until the heat death of the universe. You know, a very sore finger. And you would never see the same pattern twice. But now with a few simple links between the nodes, the number falls dramatically of potential states. You start to recognize them. And he noticed that there were 317 states that this system kept falling back towards. 317, of course, is roughly the square root of 100,000. So by connecting things together, the number falls from 2 to the power of 100,000 to 317. 317 we can deal with. It's not great, but it's better. And he called these states attractors because it seemed like the system was attracted to these states. It wanted to be there. It kept going back to the same place over and over again. Attractors are the only reason that we as human beings can even live in this universe, because everything's kind of familiar all the time, because the systems that we engage with, whether they're economic, social, biological, or political, they follow this law of attractors. By things being interconnected, the number of possible states in a system is actually very limited by the connections. And that's the reason why we all have two eyes in the front of our head. It's the reason why we don't just fall into a glutinous mess. It's the reason we hold our form is an attractor. It's the reason you can quit your job in London and go to New York, get a new job, and everything's the same. The same coffee machine, the same desk, the same pointless, endless meetings, all of these things. They're all attractors. And he noticed that there's three numbers that are important in these networks, N, K, and P. M is the number of nodes in the network, and he noticed that as N rises, the number of attractors in the system rises. And that makes sense because it's roughly root N. Then he noticed that the degree of connectivity in the network also influences the number of attractors. He noticed that as K rises, the number of attractors increases. Not only the number of attractors, but as K rises, the blinking in between, the journey between attractors becomes more chaotic, harder to predict. And he also noticed a third value, which we call bias in these networks. And bias means that if I have a node, this node here has two choices. It can send a message this way or this way. And if it sends its message this way 50% of the time, and this way 50% of the time, then it has no bias. But if it sends a message this way 2% of the time, and this way 98% of the time, then it has a huge degree of bias. And he noticed that when you increase the bias of the nodes, then you can increase N and K, and the number of attractors will still stay small. Now, all of these things are obvious to us as software engineers because this is what you've been doing your entire career. You've been balancing the number of nodes, the number of connections, and you've been biasing these nodes with things like contracts and interfaces and protocols and schemas so that they behave in a particular way. And the job of the software architect is very much to get a grip on these three things and make sure that the system behaves itself. And we call it all kinds of things. Some people call it domain-driven design. Some people call it object-oriented design. There's lots of different ways of describing and doing this. A lot of us do it on pure instinct, but everyone has this in common. This is what we're trying to balance. And so from a complexity science perspective, all we do as software engineers is repeat this simple two-step algorithm. A random simulation of our environment, which we call requirements and risk and process mapping and all of those things. I know that's offensive to some people. Followed by an NKP analysis of potential software structures. That's all we do. And that makes things much easier to talk about. And now we need to think about things in a slightly different way. And this thing called residuality theory that we're going to talk about will make this simulation more random, and it will make this NKP analysis more explicit. And it will allow us to surface what goes on in the heads of architects when they make decisions, so that we can do it better. So residuality theory is at heart a philosophical idea. This can be quite difficult for engineers to grasp because it's so low level. Basically, we live in a world, and the world is a network. It's complex, and it's moving, it's constantly changing. And we can't map this, okay? You can't draw a diagram to describe this because by the time you finish drawing all your diagrams, it's changed, it's moved, it's different. And you can't describe the whole thing the way that traditional enterprise architecture has tried to do. So what can we actually say that's true, scientifically true, about this network, rather than getting involved in speculation and conjecture? The only thing we can say is something's going to happen, because a complex system, by definition, is constantly moving. If nothing happens, then it's dead, and you can map it and send in the enterprise architects. Something happens, and we call that something X. We don't know what it is, we don't know when it's going to happen, but we do know that when it happens, it will change the system in some way. The system won't be the same after this happening. And we call this piece of the system here that's left over, we call this the residue, the leftover of the system. And the leftover of the system is also a complex system. And what can we say about it? Well, something else is going to happen. Let's say Y. We don't know what Y is. We don't know when it's going to happen. We know what's going to happen. And when it happens, it's going to change the system. But in this step, we can also say that the future of the system after Y is a function of the residue. It's a function of whatever's left over. So the residue has an impact on the future. And as engineers, as architects who are defining the structure of software systems, we cannot map these systems. We can't map them completely. We can't predict X, we can't predict Y in a complex system. But we can control the residue, because the boundary decisions that we make in our software and the way that we distribute components and the way that we link them in our software control how the software falls apart when X and Y happens. And so we control the residue of the software. And that residue is going to become the fundamental building block of our software. So what have we learned? We have this problem. We have this innocent, structured little thing inside this massive, pulsating, complex mess. What we've learned is that we don't need to map every single detail or every single variable of every single entity inside this massive, complex thing. We've learned that there's a limited number of attractors inside here, and those are the things that can actually happen, and that's what's interesting to us. And the issue with a lot of architecture is that we build for one of these attractors, which is some kind of happy path that gets described to us by business stakeholders. We want to expand and design our architectures for as many of these as possible. And so what we do is we just come up with something randomly that will allow us to tell a story about a particular attractor. And so one thing I can come up with is, what happens if a competitor drops their price? If a competitor drops their price, I'm in a new business attractor. Things have changed. The business model starts to change. Our ideas about our product and how we approach our market change, and the architecture will change. And so I ask, what's the residue? What's left over of my software architecture in this attractor? And I see that these two components have died. They don't work anymore. And I look at it, I haven't built anything yet. So I look at it and I say, if I put this little green component in here, then this architecture would actually survive in this attractor. That's interesting. So I park that over here, and I call this residue number 1. And I do the same thing again. I come up with another attractor, another thing that stresses the system, pushes it to a new attractor, and I say, does my architecture survive? And this one needs this little orange component, and I call this residue number 2. And I do it again, and I come up with number 3. And what you end up with is a new way of describing your architecture. I have my original naive architecture, which solves the functional problem, and then I have a whole bunch of residues that describe how this architecture is going to survive in a whole bunch of completely speculative attractors. This is called a residual architecture. And what we're going to do with this then is we're going to compress all of these into a single coherent architecture. And when we do that, we notice a behavior that's very interesting. This kind of architecture starts to resist things that it hasn't been designed for. It starts to survive those X's that it hasn't been designed for. And this is what senior architects have been doing. And a lot of times we would have called them negative. So you're just being negative, thinking about all these things that are going to happen. What's actually happening here is that when I identify a single residue, generally what's going to happen is that that residue will survive in a certain number of attractors. Each one of those attractors has a whole bunch of potential X's which could push the business system into that attractor. And that means that if I, as the architect, pick one of these X's to be my random simulation, which is what we're doing, then I will identify this attractor from this particular X. And if I identify this attractor, I identify this residue. If I identify this residue, I survive in all these attractors, which means my system survives all of these X's, even if I don't know what they are, where they are, why they might happen. And then the system starts to appear like it's magic. And this is a very simple mathematical leverage that exists because we have an ordered system inside a disordered system. This has existed forever, but we've never looked at it closely enough to realize it was there. And it means that I can randomly simulate my architecture and get to a result that appears to survive things that I haven't predicted. And we spent the last few decades trying to identify every X or every significant X in risk management tools when we should have been looking at the attractors, but we didn't know how to do that. There's a few caveats, though. Firstly, there's something called the curse of high dimensionality, and this means that people are generally very bad at randomly simulating their environment. And what happens is they tend to throw all their darts in the center of the circle, try to hit the bullseye. We try to be correct, and that gives us a very skewed picture of the area of this circle. And the way to get out of that is to be a little bit ridiculous. And so one of the first stressors that we should use just to make this apparent is that giant fire-breathing lizards come up out of the sea and destroy the city that you do business in. And the question then becomes not how likely is this, because we know it's probably not going to happen. The question becomes, what's the residue? What's left over of my architecture? And what this does is it exposes fault lines, it exposes cracks in your architecture, it exposes how your architecture falls apart rather than how it's built. If this is your X, giant fire-breathing lizards, then you will build a system. I mean, the obvious solution to this is redundancy in some other city. You will build a system that will survive flooding and fire and social unrest and invasion and pandemics where people can't get into the city, train strikes, things that affect the business that we maybe don't have in our risk register. And this allows us to build systems that are incredibly resilient and also seemingly magical. Kauffman has this idea of criticality. And criticality is whenever a system is flexible enough to survive in an environment that it doesn't control and doesn't understand. And it's very different than correctness. And as programmers, we're taught to be correct. As architects, we have to learn how to build systems that are not entirely correct, but they're critical. They survive for long periods of time in the unknown. And Kauffman describes it like this. It's a balance between n, the number of nodes, and k, the number of links. And so down here, we have what we would traditionally consider to be a monolith. Very low n, low number of components, very low number of connections. What's the problem with a monolith? If something stresses or hits this system, the whole thing falls over. It's very, very vulnerable and fragile. So how do we solve that? Well, we're in tech, so we have a massive pendulum swing right up here, and we call this microservices, and we have lots and lots and lots and lots of n and lots of k. And yes, it's harder to kill this entire system, but you don't have to kill it. You just have to damage one or two little nodes, and ops will have to spend 3 weeks looking in logs trying to figure out what happened. And the weight of having this level of n and k actually causes the system to eventually collapse and it dies out. And so Kauffman identifies this thing called the edge of chaos, which is a really cool thing, very popular among management consultants. And the edge of chaos means that you find a balance of N and a balance of K that allows you to survive in your environment, to survive in an environment that you don't control, but you don't really even understand. And that is when your system is critical. But not so big N and K that you collapse under the weight of trying to keep yourself alive. And what we do with this methodology is we start off, let's say, with a monolith, and we stress it with something that seems like nonsense. And when you stress a system, it has two choices. It dies or it changes. And when we stress our little monolith here, we'll break it up and we'll say, we'll need these couple of extra components. And then you stress it again, and you stress it again, and you keep stressing it until you get to the point where it starts to push back. It starts to solve things that it wasn't designed for. And when you see that behavior happening, you know you've reached criticality and you've done your job as an architect. I'll give you a concrete real-world example so that this makes more sense. So we're going to build a platform that manages fast chargers for electric cars all over the world. And the way this is going to work is that customers will go into a website, put in their credit card details, become a customer, we'll send them a little key ring home. And the key ring, when they hold it up to the charger, will send a message up to the cloud, see if they paid their subscription, send a message back down to the charger and say, you're allowed to charge. That's the naive architecture. And like all naive architectures, we put it into production. And then we start to throw these X's at it to see what could we do to make this architecture better. And this is the politically correct version that you show to management, no lizards on here. And there's a couple of things that are interesting here just to show you how this works. The first thing is the field login. Okay, so customer drives up in their electric car, holds up their little key ring, and nothing happens. And this is because these key rings are sensitive. They don't work all the time. And so that's our stressor. What's the residue? What's left over of this system? Well, you've got a customer parked in front of your asset. They've got no electricity in their car, most likely. They can't go anywhere. You've got a queue building up behind them. This isn't good. Now you're going to have people calling you. So you're going to have to take care of that in some way. And the way to do this, when we think about it, that little green thing that we add is something called ALPR, automatic license plate recognition. So what we do is, instead of having this key ring, we just read the license plate, let everyone charge. This is back in the day when electricity didn't cost so much. Let everyone charge, and then just get them off the lot so that things keep moving. And that gets rid of this particular stress. And so we've added our little green thing, which is ALPR, which massively changes our software architecture. And this is why you shouldn't build things before you do this. The next thing, stressor number 8, is damage. People are going to drive into these things. So let's have some security cameras so that we see who drives into them. And let's have some redundancy. Let's assume that on every lot over the world, there's going to be a few of these things that someone's driven into every week, and they'll be out of commission. And the next thing that's interesting is number 12. So your customer abandons their car in a slot. This happens a lot at golf courses. It's a huge problem. People park, plug in the car, and just go away for a long time. And only they can unlock this thing from their car. And you're back to the same residue. You have queues, you have stress, you have irritated customers. So how do we solve this? And we solve this using our ALPR, and we invoice per minute on a sliding scale, so that when someone does this, the first 25 minutes are at a reasonable cost, and the next 25 minutes get much more expensive, and on a linear scale, we charge them more and more and more for every minute that they're there. In that case, it's really expensive parking, and we as a business make more money than we would have if they hadn't done this. So we're good. So all of that is what happens when you start stressing this thing. You start saying, what if this happens? What if that happens? What would push us into this attractor? And this becomes really interesting then when we hit stressor number 14. And stressor number 14 is something called icing. ICE stands for internal combustion engine. It's the electric car industry's way of talking about fossil fuel vehicles. And icing is a very particular kind of behavior. In the United States, people look at an electric car and they say, the person who bought this car must care about the environment. And if they care about the environment, that means that they vote for a particular political party. And I don't like those people. And so what they do is they take their pickup truck and they park it in front of the charger so that the electric cars can't get to it, they can't charge. Then they get out of the pickup truck and they do a dance and they film it and put it on TikTok. This is true. And it spreads, and this starts happening everywhere. And the residue is pretty much the same. We can't get to the chargers, our customers are stressed. We are not making money when people were doing this. But it turns out that this is one of those stressors that is, lizards might seem ridiculous, but this is also ridiculous because no one could ever have thought of this. No one sat down in the design phase and thought that this was going to happen. It turns out that this system will survive without doing anything. And the reason is, firstly, we have you on ALPR. We have your license plate. We know who you are. You're getting a bill. You've parked in our spot. We're going to charge you whether you're plugged in or not. The other thing is we have redundancy. There's lots that we've allowed for that some of our charging things are going to be out of commission. So you better bring all your buddies if you want to really hit us. And thirdly, we're going to charge you on a sliding scale. So you'd better make it a very quick TikTok and get out of there. And this means that we, as a design, we survive this even though we didn't know it was there. And this is the behavior that you see happening over and over and over again when you treat the basic component of your software as a residue and then compress them, you start to see this behavior happening over and over again. And you might think that that's a very American behavior. This is Munich. Someone had exactly the same thought process. They said, if you're driving an electric car, there's a much higher chance that you're a vegetarian. I don't like those people. And so to show them, they stuffed mincemeat into the chargers. No one ever doing traditional architecture in their requirement specification has requirement x.x.x, someone's going to stuff mincemeat into the device. We just don't have these things. And we live in a world where these kind of things happen all the time. And we have to build our architectures to survive these kind of things if we want people to believe that our architectures have a certain level of quality. And we're not in control of that. We have to be able to survive these things. The question then becomes, how do we integrate all of these residues together without destroying each one of them? Because they're all going to constrain each other when we push them together. And we do that through something called contagion analysis. And it works like this. We design our architectures and they look something like this. And we try to isolate change in our architectures. Try to isolate things that we know are going to change, like database connection strings, which most of us don't hard code anymore. But the horrible truth is, no matter how good you do this job, you don't know what's going to happen in the future. And so you put this innocent little thing back into this horrible, complex mess that is real life. And sooner or later, some form of stress that you weren't aware of turns up in the environment. It can be mincemeat in your devices. And we usually think in terms that this thing is going to hit one of our components. And we try to encapsulate change inside that component. The horrible truth is that when these things turn up, they usually hit more than one thing. And so here we can see that we're hitting component C and we're hitting component G. In network science, which is one of the sort of key tools of the complexity sciences, when a stressor has a relationship between C and G, when one node has a relationship with two nodes in this way, it's implied that there's a relationship between C and G. In software, we have a word for this. We call it coupling. But if you look at our architecture sketch here, we didn't see that coupling. We've separated it. We don't see why there's no functional coupling here. And so we miss it. And it turns out that there is a coupling between C and G, but when you investigate a system in the way that we're doing it through the use of stress rather than requirements, what you end up with is this spider web of invisible coupling. And this explains why the job is so hard, because this thing is what causes change and stress to ripple through our systems and touch dozens of components and surprise us all the time. This is why the job is hard. And because most of these relationships aren't functional, because we're quite good at catching functional relationships, these lines, this spider's web, is an expression of non-functional requirements, which means that we can actually capture things here in a way that's much more efficient than chasing some poor business stakeholder down a corridor shouting, "Tell me your functional requirements," which is what we've been doing for too many years. And so the way to do this is through something called an incidence matrix. And so networks are lovely, but drawing networks is hard. And you've seen my drawing skills. And they get very big and very messy very quickly. And the best way to express a network is in a matrix. And so we have our nodes in the network are firstly all our potential components, which are the columns, and all of our stressors, which represent the world outside. All of our stressors are the rows. And every time a stressor touches a component, that's a network link, we put a 1 there. And whenever we have 2 1s in the same row, here we have 5 1s in the same row, that represents this hyperliminal or invisible coupling between those components. That means these components are coupled. And then we look at this thing and we say, did we know that? Did we know that these things were coupled? What is it that couples them? In this case, when we look at it, you can see it's a server failure. You can see that they're coupled because someone's put all the components on the same server. Maybe we want to change that. And what this matrix gives us is it gives us a bunch of clues about the quality of the compression, the quality of our architecture. And we can first find all these big numbers. You see a 5 here and say, why does this thing take out so much of my system? What can I do? What can I refactor in order to make the system less vulnerable? Do I need redundancy here? Or have I made a mistake? Have I put a single point of failure into my architecture? In this case, we have. And down here, you'll see we have a 4. We pick on the highest numbers first. And you can see that this particular component is getting hit a lot. And that's a sign of, 2 things. One of 2 things. Either we've put too much into this component and we need to refactor and make it less vulnerable, or this component is so crucial in our network that we need to protect it. We need to take care of it. We need to make it redundant. We need to put it in a different data center, make sure that it can always run and have alternatives for when it does get hit. And that improves our architecture. Another thing that comes out of this is that we see that those components like this one and this one that have exactly the same pattern of response to stress can live and die together. And so we could push those things into one component and our architecture would not suffer for it. And therefore we can reduce N. And what we're doing here is we're constantly trying to reduce N, reduce K, and figure out what do we need to do with P in order to get a balance on this thing. And this is making the NKP analysis that we talked about earlier very, very explicit. And there's no ceremony around this. There's no massive library of terms that you need to learn in order to understand it. And you can do this with components, you can do this with flows of information, you can do this with functions. Last year we showed how you can do it with bounded contexts in domain-driven design in order to question and interrogate and make sure that when you compress your residues, that your architecture is still going to stand up and still going to work. And so if you add all of these 1s up and divide it by the number of nodes, you actually get a value of K, and that's what we're trying to do. We're trying to calm the system down. All of you who design systems are already doing this work today. The problem is that the only thing you can do is draw sequence diagrams and activity diagrams that describe the static architecture. All of this noise that we've talked about, all of these residues, all of these 1s and 0s, you as the architect or the system designer are forced to carry that in your mind all at once. And that's very, very difficult. And that's why when we go to senior architects and say, how did you make your decisions? They're like, I don't know. There was a lot of noise in here. And stuff came out, and I'm usually right, so I went with it. This allows us to be really explicit about how we're making decisions about the structure of our software systems. And finally, all of this allows us to do something which is entirely new for architecture. It allows us to show the world that we've done something useful. That's a huge shock for architects. This is going to change things. We have our naive architecture. And what we do is we take a list of stressors and we use those stressors to transform our architecture via the matrices into this residual architecture. So we have two very different architectures. And what we do is we create a second list of stressors that neither of these systems have ever seen before. And so now we're going to test both of these systems with a bunch of X's, a bunch of unknown unknowns. And what we do is we push all of these stressors at the naive architecture and we say, did it survive? If it survives, it gets a point. If it doesn't survive, it gets 0 points. We add all of those points up and we call that number X. We do the same thing for the residual architecture. If it survives, it gets a point. If it doesn't survive, it gets 0 points. We add all of those numbers up and we call them Y. When both systems don't survive, we look at them both and say, which one survives best? And it gets a point. And then we calculate this thing called the residual index, Y minus X. So I'm saying, does R survive better than N over S? And that gives us a number by definition that is between -1 and 1. The size of the number doesn't matter. What we're looking for is direction. And if the residual index is greater than 0, that means that we've moved this architecture towards that line of criticality. We've produced an architecture that is more critical than where we started. And you can do this in an iteration, in a loop, and you can see that you're constantly moving towards that line. You're constantly improving the quality of your architecture. And you do this, once you've done this, you can say, hey, look, we did a good job. And up until this point, we haven't even mentioned cost. So one of the first things, and many of you out there are thinking this will cost too much. And that's an instinct that's been built into us over the years where we start to bias towards cost before we build anything. And it's led to a situation where we bias towards cost before we think. And that's dangerous when your job is thinking. And so a lot of times I'll talk to architects and say, no, we can't think about that because it would cost too much. And it's like, thinking costs at most a couple of calories. Okay, I'll give you a bit of chocolate, and we'll be quits. It doesn't cost anything to think. So at this point, we have an architecture. Now we can go into that discussion about enterprise risk, which is a different thing than what we've been doing, and cost. And then we can scale our architecture back down if we need to. But at least we'll have discovered the boundaries and the fissures and the weaknesses in our architecture. We will have an architecture that we know how it falls apart. And that is what we have to deliver as architects. I saw a video a few weeks ago of the earthquake in Japan, and this is just a huge number of buildings that just shook, and they knew exactly what they were doing, the people who built them. They didn't fall down. And those people were thinking about the residue of what they were building. They weren't thinking about how pretty it would look or how functional it would be. They were thinking, what's left over of this system when it's exposed to a massive amount of stress? And it took building architects, 10,000 years to get there. We've only had 60 years. And hopefully this is a step towards the same thing. And that's everything from me for now. This is Residuality, Cat. You can reach me here on these things. Thank you for coming. And you can come up if you have questions.
We can do a Q&A with microphones further.
Yeah, let's do a Q&A. Someone's going to ask about cost, someone's going to ask about complexity, and someone's going to ask about agile.
Thank you. When you showed your matrix of the stressors, I think it's difficult to think of the possible ways things can fail. Like you have to have a massive dictionary of stressors. Otherwise, you can't even analyze how the components are coupled and why they can fail. I'm thinking, why don't we define properties of the system that we would like to have? So instead of defining how things break, can we define how we expect these components to behave, and then think, what happens if, I don't know, it times out, so it's not responsive. So responsiveness is a property of the system I want to have, instead of thinking in ways why the responsiveness can be affected.
Okay, on a philosophical level, you're asking about the difference between analytical thinking and synthetic thinking, and I'm very strongly recommending synthetic thinking, which is we have these conditions, what happens then, rather than here's the behavior, how do we work backwards to what we want? The short answer to your question is that we've had patterns in our industry for over 40 years as a standard way of working, and architectural quality is still too weak, so we need to try something else. And also because of something called black swan theory. When you say that I want my system to have this property, so when you build a flood wall and say the highest flood we've ever had has been 5 meters, so we're going to build a 5.1 meter wall to save money, the next flood will be 6 meters. That's the way complex systems work, and we get caught out all the time. So trying to predict where we should be is always dangerous in a complex system. So we have to make sure that we have this property of criticality. And what you're seeking is correctness, which is the programmer's way of looking at a complex system. If you try to seek correctness in a complex system, you're just going to be sad all the time. Because by definition, they just keep moving and they keep changing and they make fools of us all the time, which is why our requirements, is why 20 years ago we had an agile movement that said this thing with requirements, it isn't working. And this is the explanation as to why. It just keeps shifting all the time. And it will catch us out. I think we had another question back here.
Yeah, so if I were to sit down and try and think of all the X's, all the stresses of my system, I feel like you could sit there for quite a while and think of many, many things. But in practice, how would you decide which stresses to tackle? Because there's only like so many hours in a day. How do you pick which ones are actually the most important?
Yeah, so we don't. So the first rule of doing this work is no probability, no ranking, because that's one of the major failings, I think, of enterprise risk management. When you go into an enterprise risk management scenario and you want to put probabilities and weights on things and say what's more important, we don't have access to that science. It's all a lie. So what you end up is expressing the bias of the most powerful people in the room about what we should work with. And that is not the same thing as the future of the complex system that we're working in. It never is. That's why we have architectural failure. What happens is, and it takes a bit of practice, not everyone can produce very long stressor lists immediately. It takes a bit of training to understand what we're really focusing on here is that our software has a relationship to the environment around it, and we need to be very explicit about that relationship. What you'll find is that as you move through your stressors, this behavior that I've shown is that you'll find that suddenly you have a stressor that doesn't break the system. And then you'll get another one that doesn't break the system. And then you'll get 5 in a row. And that's a sign that you've reached criticality. At that point, you get bored and you go and find another architect and you say, can you break this? And they'll break it a little bit, but then they'll end up in the same thing. And you run out of energy because you can't stress it anymore. And that's a very clear sign that you've finished. And it stops analysis paralysis. And if you keep going and you keep going and you keep finding stressors, then the system is chaotic and you shouldn't build software for it yet. You should get someone else to do it. But it's very, very rare that we see that kind of system. So.
Are there any other questions?
Okay, I'll hang around here for a bit if anyone has any questions, and you can reach me at these places. Thank you.